So now on to Newton's second law of motion.
We are indeed, but just quickly,
Yeah?
I'd like to have a special birthday message to my friend James here.
Oh, thank you.
Yep, it's his birthday very soon. Celebrated yesterday. Went to your favourite restaurant, had some of your favourite meals, went to a few clubs all night, met the DJs, put on your favourite songs, in fact.
Yeah, it was really good.
Really good night, really good night.
Oh.
Enjoyed it.
So, why wasn't I invited?
Oh, it's not really your thing.
Oh, okay. Anyway, Newton's second law. It's quite good because this isn't just stop at one.
No,
It's got round two, and it uses the first one.
it does. The idea that if there's no force acting on anything, there's not going to be any acceleration. It will either stay still or it will continue at a constant velocity if there's no forces acting on it. Except now it's to do with momentum. So what say I actually read you the definition?
Alright.
Word for word, his second law.
Mm-hmm.
The rate of change of momentum of an object is directly proportional to the resultant force acting upon it.
Right.
So it's to do with momentum and proportional. Now, how on earth do we get to that?
Okay, well, you remember the equation we had where change of momentum equals Ft.
I do remember that. That was last video.
It was. Now, if change of momentum equals Ft, then we can use our other equation of momentum, changing, which is
mv minus mu, where v is the final velocity, so that's your final momentum. And that's your
equals
initial.
Ft. But we rearrange it, do it over t.
This is sort of looking like what his law is, because it's equal to force.
Yeah, we came there.
So, I like it.
So now I want to expand, we want to factorise that top bit. So we have m lots of v minus u, to expand that, we'll get that. Over t equals f. But wait, you noticing something?
Yes, I've got it. Your black pen's better than mine.
No, that's not what I was expecting. It's v minus u over t is acceleration.
Oh, I'll give you that.
So that means ma is proportional to f.
It looks a bit like a fish.
It does look a bit like a fish, but it's a proportionality sign.
But I've done f equals ma in
Yeah,
S,
you used it before.
and I don't remember the fish.
Oh, well, that's if you didn't use a fish. When you have a direct proportionality, you can say that ma would equal f with a constant.
Well, that's another problem though, because I don't remember using that k in f equals ma either.
Ah, well, you did, but you just didn't notice.
Why not?
So the k is used when it's defined, you silly, with the Newton. So what's the definition of Newton, Wayne?
Well, I've got this.
Right.
1 Newton
Mm-hmm.
equals, it's the force required to give a 1 kilogram mass an acceleration of 1 meters per second squared. So if we've got this k, 1 over 1 is...
That's one.
K equals 1 over 1. The 1's cancel, so it equals 0, yeah?
No, that's one, Wayne.
Oh yeah.
Yeah.
Silly.
So that means there's always one, so you can just forget it's there. Just pretty handy.
And that's Newton's second law in a nutshell.
Ta-da! And you use that quite a lot. And you use a few newish things. Not very new. Mass. I think you've heard that one before.
And weight.
And weight. You've got a new way of describing it using inertia. And inertia is how hard it is to move something. You have more inertia, harder to move, and it's to do with mass, because higher mass, you're harder to move, higher inertia.
It'd be much harder to kick the earth than it is to kick a football, for example, because of the mass.
Yeah.
What about weight?
Well, weight's the same pretty much as it always is. It's the force because of the acceleration towards the centre of the earth.
I found a neat little question on this. Do you want me to give it a go?
Alright, let's do it.
Alright, I'll read it to you.
Okay.
Now it's all about accelerating an oil drop, because
I like
why wouldn't you
accelerating
accelerating an oil drop?
All the time.
So in an experiment to measure the charge of an electron,
Right.
an electrical force of 2.8 times 10 to the minus 8 newtons.
That's not very many.
Doesn't take that much to move an oil drop actually. Is exerted upwards on a charged oil drop
Alright.
of mass
Oh, there we go.
3 UG.
You speaking drummer?
Not quite. If you
Oh.
remember, UG is the weird U shape.
Oh yes, micro.
Micrograms. And that's how much this oil drop weighs, and it says what is the acceleration of the oil drop.
There's a few things to think about here. The first thing, I don't like working in UG.
In fact, you shouldn't work in UG, because then you're acceleration will be wrong because you have to bring into if this Fk equals ma. If your mass is in something other than kilograms, it can throw off everything. You have to work.
Your K would no longer be 1. So let's sort that out. We need to get this into kilograms. So first, we need to get rid of the micro. So what is micro, Wayne?
Bigger nanomicroscopic Pikachu.
You're doing what?
10 to the minus 6.
Oh.
So if you do 3 times 10 to the minus 6, you're going to get grams. But that's not quite right.
That's not quite right. Mass is weird. It's the only unit in physics and anything where its SI unit, a standard unit, is kilograms. So we need to put that on. But that's sizing that into the plus 3, so it becomes 3 times 10 to the minus 9. Absolutely.
So that can now replace this mass.
It can.
3 times 10 to the minus 9 kilograms.
Absolutely. So we have our little oil droplet. There he is. Very happy.
He's very happy.
But he's going upwards, but when I jump, like that, what pulls it down again?
Well, that's gravity,
Yes.
and I don't think this happy face can ignore gravity.
I don't think it can. It can try.
So it's going to have a force acting downwards, and that is going to be the weight. Now, weight, how do we do that? We did it at AS, didn't we?
We do, yeah. So we know the acceleration of gravity, don't we? That's
9.81. Gravity's a pretty quick one, isn't it?
It is, and that's our acceleration. I think we can use F equals ma, won't we?
You can.
So, give me that. F equals our acceleration, doing it am because it's morning, times our mass, which is very small.
Yep. 3 times 10 to the minus 9 kilograms. Is that the same as 3 nanokilograms? I think it is.
I think it is.
Anyway, yeah, so you got that,
Yeah.
times that will give you this force, which will be the weight. So if you'd like to do that.
I would like to do that, and it may take a few seconds. It's a bit of an awkward calculator, so yeah. Do you want to do a bit of your stand-up you've been working on?
Stand up, yes,
Yeah.
I am standing up.
So that's a good start.
Okay, so, joke. An infinite number of mathematicians walk into a bar. First one orders a pint, second one orders half a pint, next orders quarter, then an eighth, then a 16th, then 1/32 of a pint. And then the barman says, "You're all idiots," and he pours 2 pints. It's a maths joke, I figured you'd get it.
And we have our force.
That's the force, and that's acting downwards, so it's acting against this one.
Oh. Yes, I did it right.
So overall, we're doing this F equals ma, we're working out a, we're going to have F over m equals a. Now the m we already have, but the force, if we've got that going up and that going up, we treat them as vectors, we can just take them away from each other, or add them together, but one of them's a minus.
Absolutely. So, as it's going down, this is a minus, we can do that now.
Yep.
Which will just be 0.14. Exactly.
0.14 times 10 to the minus 8
Absolutely.
over the mass,
which is very small.
3 times 10 to the minus 9, will give you an acceleration.
Is sure this one?
That's a naught, not a 6, I should just clarify. And that's a naught, not a theta. But, yep,
Is
okay.
this one?
Yep.
Alright.
Okay.
So, okay, all the jokes well. Right, you ready?
Okay, I love it.
So, Einstein, Pascal and Newton were playing hide and seek. So Einstein was a seeker, you know, go off and hide, just counted 10. Counted. Pascal ran off to hid, but Newton just stood there. When Einstein opened his eyes, went, "Newton, I found you." And he went, "No, you have found 1 Newton per square metre. You found Pascal."
Ha! I get it,
It's good. Yeah.
So it's 0.47
0.47.
metres per second.
That's not very fast.
Now, what do you expect of these oil droplets? They're all lazy.
Oh, very happy though.
Although happy. As long as
Yeah.
they're happy, I guess.
Yeah, that's all that matters really, isn't it?
Yeah.
And that though, we should probably get
On
the next
to the next
video.
video.
Yeah. One more thing, Wayne.
Yeah.
The birthday's not today, it's in January.
Oh, perhaps it's Gil's birthday.
Maybe.